Hello everyone, welcome back. In this lecture, we are going to talk about the very thing that we were talking about in our last lecture, that rhoCentralFoam does not work well when the mesh is non-uniform. That means it abruptly changes the resolution similar to the mesh that we get from snappyHexMesh. Let me show you by copying this one of the example that is present in OpenFOAM tutorials. This is an example of forward step. So let me run this blockMesh and rhoCentralFoam. It has completed. Now we can just open this using pimpleFoam. I think we need to change something. Since it was not saving all the solutions, I have to change the control dict. Go to system, control dict. We do not want to purge any solution. So remove this and clean everything and rerun. Now let's look at the solution again. Here you can see that the solution, here we have the inlet, and since the flow is compressible, so therefore the presence of an object creates a shock wave because that's a step. So you can see various shocks that starts from this due to this corner as well as due to this vertical wall against the flow. So you can see due to this corner we first have this wave and then it get reflected from here because we have a symmetry boundary condition here as well as here, and then it comes back. This is what we are observing. Similarly, when it hits here, it again creates another reflection, and you can see various pressure and velocity waves. But the thing to note here is the mesh is uniform. Here we can again generate a non-uniform mesh and try to solve this, but that will be very simple. So instead of this, let's try flow past a certain obstacle. We'll try to solve this using rhoCentralFoam, then we'll solve the same problem using rhoPimpleFoam, and we will see a clear difference that rhoCentralFoam won't be able to solve that kind of flow. Let's get started. Let me first open VS Code. So let me clean the old simulation, and this is the folder. Here we'll first copy one of the geometries. If we just look at blockMesh dict, just the blockMesh, you can see this is L-shaped domain and all uniformly distributed. Instead of this, we are going to consider a bigger domain. So we'll use this particular domain. Here the vertices are this 0, 1, 2, 3 and 4, 5, 6, 7 is the another layer, and this will be the hex block. And since we don't have these other hex blocks, therefore we have to remove some of the points from here. We can copy from one of the previous simulations. So here we have these patches sides, symmetry planes top and bottom, and then inlet and outlet. Here if we now run blockMesh, then we'll have this particular domain which looks something like this, and the domain is again uniformly distributed. But here we'll put an obstacle and then use snappyHexMesh to create mesh around that object. In order to do so, we'll first create an object. I already have this object with me. That's a simple square that we have used in our previous tutorials that are present in our YouTube channel. Let me copy that. I have copied the STL in the try surface. So let's visualize this particular object. In pimpleFoam, I'll open this. So you can see it bisects this particular domain, and the shape is little bit different. It's not a square anymore. It's an arbitrary shape object. Now I'll use snappyHexMesh to create a mesh around this particular object. In order to do so, we can copy any of the snappyHexMesh file. Here I have copied these two files. This is nothing but the existing mesh quality dict. It copies all the values from the existing mesh quality and use them to maintain the quality of the mesh. And here this is a generic snappyHexMesh dict. Here I declare this particular variable cylinder, which is taking this particular STL file, and then all other variables are standard. For example, this refinement surfaces. Using this, you can define the refinement around that particular object and various other features. We'll have another tutorial to discuss all these parameters in a meshing playlist that will come in a few weeks. But these are some of the parameters that we are going to use. Let me just go through all the parameters so that you know what this particular file looks like. In the snap control, we have all these parameters, and we are not creating any kind of layers, so these are not required. And then at the end, we are including the mesh quality dict to make sure the mesh quality is something which is standard in OpenFOAM, and that's why it takes the values that are present in OpenFOAM repository. Then this merge tolerance is the standard tolerance. Now, if we run snappyHexMesh, it is completed. Let's look at the mesh. You can see that the hole has been created, and now you can see the mesh as well. It is pretty good because we have added decent number of fine layers before it moves to another resolution. So it is not that abrupt change of resolution that generally are created in case of mesh created from snappyHexMesh. We have made sure that it's not that abrupt, but anyway, it is abrupt compared to a uniform mesh. We'll look at the boundary conditions. Let's look at the various boundaries that we have and the boundary conditions here. For the pressure, we have inlet, outlet, bottom, top. The obstacle, let's see sides. These are the sides, and bottom, top are symmetry. These are symmetry, and the inlet and outlet as is, and then cylinder. This is cylinder. Similarly, for temperature, we have inlet, outlet, bottom, top. Obstacle is cylinder, and default faces are sides. So this is cylinder, these are sides. Let's look at other properties as well. We can also have turbulence property, even though here we have laminar, but we can have different kinds of runs models that can be included in rhoCentralFoam. But for now, we are just doing this laminar simulation. And here, by default, this mu is 0 here, but to make it a little bit realistic, we are going to add a little bit of viscosity. But rhoCentralFoam works without any viscosity as well. Now we'll run rhoCentralFoam. There was some problem. Patch type is empty, but it's not empty there. We have to change here. This should be empty. This is usual practice because in snappyHexMesh you cannot have empty patches. Therefore, you have to have a patch and then change it later. There was some problem. The solver is not stable because the values that we have used here are not realistic. Let me change this. The pressure value is 101325. Similarly here should be 101325, and the pressure also should not be a fixed value. This should be zero gradient, and the outlet should have a fixed value with value equal to this. For some reason in the first step this was different, and for temperature here we are going to use 300, and the inlet has a fixed value 300, and these two also 300 and 300. And then velocity, this we are going to keep for now low velocity. We'll see whether this works or not. And the cylinder has a, let's keep this slip for now. And now let's run. E not found. Here in the solver, let's add E. Maybe it is asking for E because we added this. So let's look at the error again. The error says that in the solvers, entry E not found. So in the solvers, maybe here we can add one. Now this seems to work. Let me decrease the output time steps by small amount. Here it is. Let's make it 0.001. We have data, so let's look at them. You can see that how the pressure shows a lot of error when the resolution is changing. You can see this in all the cases, in case of velocity as well as in case of temperature. Now let me run this. Remember that the cylinder has a slip boundary condition. I'll just run pimpleFoam. For pimpleFoam, we just have to change the scheme. In the control dict also, we have to write, instead of rhoCentralFoam, we have to write a rhoPimpleFoam. And in case of the solver, here also we have to write the pimple solver. This is how the pimple solver looks. We can have a multi-grid solver and some parameters to control the pimple iterations. Now, if I clean everything and run rhoPimpleFoam, let me kill this and visualize the result that we have so far. Here you can see you still have those errors, but these errors are much less compared to what we have seen in case of rhoCentralFoam. And in case of velocity, you have something like this. Now let me add no slip boundary condition and see. This is not a realistic flow. That's why we have something like that result. But when we have a no slip boundary condition here, now run this again. Along with the no slip boundary condition, we also need to change this velocity. It was 0.1, so 0.1 comes in the regime of incompressible. That's why it was not working. So let's also try this with rhoCentralFoam as well. Let me undo this, and for the scheme as well, and in the control dict, rhoCentral. Now let's run this rhoCentralFoam. Clearly it did not run. The initial temperature was negative. Now let me change this to rhoPimpleFoam, the new scheme. It is for pimple, and similarly for the solver for pimple, which is this with the pimple loop and multi-grid solver. Now let me again clean everything and run rhoPimpleFoam. Clearly the rhoCentralFoam does not even work with the higher velocity because the errors were so high. That's why I ran it with 0.1 meter per second, even though it was not in the compressible regime. But you can see the errors were high. But in case of rhoPimpleFoam, we saw that with the lower velocity, you were getting some errors because it was incompressible, but still it was running as a compressible flow. Now, here we have 2 time steps, so we'll wait for some time to get more results. So far we have results for 5 times. Let's look at them. Clearly it looks much better now. Here we still have errors, but these can be resolved by making a mesh better and by making sure the time steps are accurate. But you can see there are no errors which are accumulating due to this change of mesh resolution. And in case of velocity also, you can see a tiny wake region, and in case of temperature also, we see some kinds of waves that are originating due to this particular object. Clearly rhoPimpleFoam works much better. So this is recommended for subsonic flow. So if it is supersonic or hypersonic, you should use sonicFoam. Let's stop here. So I hope you have learned something in this particular lecture. And if you like the content of our channel, then please like, share and subscribe. Thank you. See you again.